Hi everybody. This is going to be probably two short lectures. It's chapter 17 called Equilibrium. Equilibrium is a condition in which reactants turn into products and the products in turn will react to form the original reactants. So we've done a lot of problems this year where reactants turn into products. We've balanced, we've written the right chemical formulas, we've decided what kind of reactions they are, single replacement versus synthesis. Now what we're going to see is a condition of equilibrium that exists. So this is something we haven't seen before. Double arrows are used in an equation to represent what we call a reversible reaction, which means it occurs in the forward direction and it occurs in the reverse direction. Consider what happens when nitrogen and hydrogen gases are mixed. So nitrogen and hydrogen. Initially, there is no ammonia, but as the reaction proceeds, ammonia is produced. As the forward reaction produces ammonia, a small amount of ammonia will then decompose, forming the original reactants, nitrogen and hydrogen. So here is ammonia, we're showing with a single arrow, reproducing the original reactants, nitrogen and hydrogen. Over time, the forward reaction will slow down as reactants are used up. The reverse reaction will increase as more products form, and eventually we reach a state of equilibrium in which the rate of NH3 forming will equal the rate of N2 and H2 combining. So we represent equilibrium with a double arrow, and what we're saying is that as nitrogen and hydrogen combine to form ammonia, ammonia will decompose and form nitrogen and hydrogen. Although the rate of the forward and reverse reactions will equal, it does not mean that the concentrations are equal. We show this in a graph. Originally, nitrogen and hydrogen react, they get used up. Initially, there is no ammonia. The rate of the forward reaction will slow down, less collisions. The rate of the forward reaction, or the reverse reaction, will also slow down over time, and eventually we reach a state of equilibrium, which is signified by the lines leveling out, which represent concentrations. Notice the concentrations of the three reactants and products are not equal to each other. They could be, but they don't have to be. There are different types of equilibrium. A solution equilibrium is where the solution is in equilibrium with undissolved solute. In order for solution equilibrium to exist, the reaction, the system, has to be saturated. It has to be holding all that it can hold. If it is an unsaturated solution, all that's going to happen is more of the sucrose will dissolve. In a saturated solution, the rate of dissociation will equal the rate of crystallization. So it appears nothing is happening in the system. But at the boundary, there is still undissolved sucrose going into solution, and there is dissolved sucrose crystallizing out. Phase equilibrium, we have to have a closed system. As CO2 bubbles out and fills this space, there is CO2 that will go back into solution. So the rate of the CO2 leaving equals the rate of the CO2 dissolving. This is the weird part. In principle, almost all reactions are reversible. To some extent, under the right conditions. In practice, one set of components is so favored at equilibrium that the other set cannot be detected. So if you think about dynamite and dynamite exploding, there is a very, 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 very theoretically small amount of product that in the reverse direction will go back and make the original dynamite. But in reality, we're not going to detect that ever happening. But theoretically, it could. So that takes care of the first lesson, and we will continue with this tomorrow.